everybody. I hope everybody knows that this next 45 minutes you're going to hear a lot about physical AI and robotics. But before I get started, how many people have heard about physical AI and robotics by way of hand? Okay, so you're in for a treat. We have an incredible panelist here. My name is Ganesh Sivaraman. I don't know whether the slides are actually getting projected. Let's see. Yeah. Okay, so my name is Ganesh Sivaraman. I'm part of NVIDIA. I lead the Omniverse Microsoft partnership. So for those who don't know what is Omniverse, it's a simulation platform. It does world-scale simulation. We'll go into a great depth of what that means and why we are here as part of the panel. We have distinguished partners of ours from Microsoft, my colleague Teresa from NVIDIA, and then our partner Wandelbots and Stefan is here. So with no further ado, I'm just going to let our distinguished panelists introduce themselves. Aaron, do you want to take it away?
Yeah, so really excited to be here. I'm with Microsoft. We're not a product group, we're a solution architect team, and we work directly with customers across the industry, whether it's manufacturing or energy. And we're seeing this bloom of demand for physical AI. They want skills that are adaptable and can react and act and make improvements in their facility. So with that, we've been working with a lot of robotics developers, and we've determined that there's some things that are holding it back, the skill development, and that is a data scarcity problem, and then a robotics developer velocity problem. And to help with that, we're trying to bridge the different computer systems that are involved here, provide the infrastructure foundation, provide the pipeline and foundation, and be this real to sim bridge. But really, we're providing some plumbing. And so some key steps in developing a skill for a robot is to collect data off of a real robot that can be used for training, but also evaluating its behaviors and its progress, using simulation to increase the size of the data set that's available, train on cloud-based GPUs so that you can scale, you can parallelize, and you can achieve outcomes at a greater scale, but also evaluate those things in a simulated environment before you ever deploy back to a real environment and finally deploy. But each of those steps ensure that there's going to be a quality skill that gets developed, and if we can increase the pace and the movement through that iteration life cycle, then we can deliver skills at a greater pace, and we can manufacture those skills. So that's what we've been trying to tackle over the last little bit in partnering with NVIDIA, with simulation and Wandelbots in deployment.
That's awesome. Thank you.
Yeah.
Over to you, Teresa.
Yeah, so I'm Teresa. I'm a solution architect at NVIDIA. So I do a little bit what Aaron also do, but for NVIDIA. And as you might know, NVIDIA doesn't really build robots, but we are partnering with a lot of companies who are building robots, or companies who are building applications and software and hardware to help people and to help robotics developers. And so my role is really to work with our key partners and customers to help them integrate NVIDIA technology. And NVIDIA itself, we're focusing also on building full stack frameworks and libraries to help people in this domain. But obviously physical AI is a complex topic, and it's hard to develop as well. And so we have technology across what we call three computers. So this is our AI frameworks, software and hardware, simulation and data generation technology, and also all the way until the runtime and the efficient type of compute that we also need to have on the robot. And so we work with a lot of these companies that you're seeing in the video to basically help them integrate the NVIDIA technology and accelerate their development paths as well. So yeah, pretty excited to be here along with the rest of the panel to talk a little bit about the challenges, but also some of the really exciting things that we're seeing in the industry.
Thank you, Teresa. That's awesome. Over to you, Stefan.
Thank you. Thanks for having me. Great to be here. Welcome, everybody. My name is Stefan. I'm the Chief Product and Technology Officer at Wandelbots, a German-based software company. We build a software platform called 𝗦𝗲𝘀𝗀𝗶ecie that unifies robots from different OEMs into one software system and platform, which then provides a unified operating system, developer tools, and different other convenience tools for engineers to work with those robots. We have, as you mentioned, a partnership with NVIDIA and Microsoft, where we also integrated our system into Omniverse. So this can also be, those robots running on our system are simulation and of course also AI ready. The video I brought with me, what we see here is what one of our customers did with 𝗦𝗲𝗀 and Omniverse, a greenfield investment scenario where a new automation line was being built up using Omniverse to build up the environment with the robots, including of course the programming and commissioning of the robots totally in a virtual environment. We see different brands being used here. And also we see a relatively complex pick and place step in just a minute with a flexible part where reinforcement learning in Isaac Lab was used to bring that to life. And happy to report that this is now also in production in a physical factory in Germany making EV car batteries.
That's exciting. That's awesome. So thank you, everybody. That was really exciting to get a context setting and introduction. So before we dive deeper into the panel itself, let's just set the context. What do we mean by physical AI and why it's such a big deal? So if you look at the whole ChatGPT moment and the Gen AI and the Copilot and the Agentic AI that we talk about, it all actually started off 10 plus years. And this is something that Jensen has been talking about a long time, NVIDIA has been front and center, which has all been around training AI models using text, images, and videos. And that's what we see as the primary wave of AI that we are right in the middle of it. And even at Ignite, you see a lot of things related to agentic AI and how you can actually train models. When we think about physical AI, it's actually taking the AI and applying it into the physical world, the world that you and I and we all live, breathe, and we operate. So how do we think about what is that going to look like? And that's what the distinguished panelists were talking about, all the different ways of doing reinforcement learning, imitation learning, training robot brains at scale that are safe, secure, that can actually interact with humans. They can actually become a very formidable force to do a massive amount of tasks quickly. So the way we think about physical AI is essentially training models, physical AI models, not just relying on text and videos. That's what we did for the Gen AI and everything that you see as copilots. But we are actually using it to take models to the next level where the physical AI models can actually take actions. You can assign a task and they can get the job done. And that's what we mean by physical AI and training those massive models. And the panelists are going to get into more details of that. And once you actually are thinking about from that perspective, you can actually truly apply those new physical AI models across different industries. And some of the examples that Stefan was talking about, the battery EV, so it can be in manufacturing. We see that in data centers. You could actually even see it in warehouses, picking and placing and packing things. So the possibilities are infinite, and that's what we are truly excited about. And the opportunity is really massive on how we think about taking the next big leap and step towards physical AI. And the way we, from an NVIDIA perspective, and I think Teresa briefly touched on this, the way we are solving that massively complex problem and a huge opportunities is in 3 different computers. So the first computer is, and I think Aaron and Stefan also touched on this, it's all about simulating in the virtual world. And that's what Omniverse is. So Omniverse is this massive simulation platform that is physics-enabled, physics-aware, following the Newtonian principles, and you're actually training things at massive world-scale level, right? So it's not just one line or just one cell. It's all of that, how they actually coexist and cooperate at a factory scale. So when you're thinking about like 1 million square feet, how is it actually going to operate? So that's what world-scale simulation that Omniverse is. The second computer is about training models. And of course, a lot of models, LLMs, are being trained today, and that's where our DGX computer comes in. And then the third one is, once you have trained all of these models, you have to actually deploy them. That's what we call as robot brains, and actually that operates inside a machine or at the edge, and that's what the AGX is. So this is how NVIDIA thinks about it, and we are very closely partnering with Microsoft. All of these computers at different phases and evolutions and roadmaps are all available also on Azure. So that's why we work very closely with Microsoft to make this happen and supercharge the ecosystem so that they can get started quickly and easily, and we're going to touch into that as well. So just wanted to help people, have a grounding of what we mean by physical AI, how we think about robotics, and how our partners are engaging with us. Okay. So with that, let's dive right into some questions. So I think it's the open question to all of you guys. So what are the kind of the big challenges or opportunities that you guys are seeing? And any one of you guys want to take that?
Yeah, I'd like to take it. So I think there's a shift from research into engineering. And so a robotics researcher has developed these workflows, whether it's reinforcement learning or it's imitation learning or it's synthetic data generation. And they've proven that functions to produce a valuable skill. But they're doing it at a relatively low scale. So for locomotion, if you want to teach a robot how to walk and navigate a room, they might prove that a robot can walk on flat ground by training it in reinforcement learning on a local PC and then deploying it in a sim, maybe to a robot. But they can prove that workflow out. The transition that we need to make to produce the number of skills required for these robots to be valuable to an end business unit is far greater than that. So just for locomotion, beyond walking on flat ground, they're going to need to be able to walk upstairs, non-smooth surfaces. They're going to have to be able to hold and lift things. All of those are different skills that it's going to need to be able to train on. So we need to create this flywheel for robotics engineering teams to work together to produce real-world data, to simulate that data, to be able to submit jobs to a queue and schedule those jobs in the cloud so that each of those different versions of what they want to train are running through a GPU simultaneously. And that same robotics engineer is now working on another task. They're not waiting for that job that's occupying their local PC to produce another configuration, another run. And then they need to evaluate quickly. So simulation becomes part of CI/CD. So in the cloud, they can visualize that policy running in a simulated environment before they've ever deployed to a real robot to make sure its behavior is going to be appropriate. And then they can even deploy that to hills. So push that down to the edge, run it on a Jetson PC connected to a GPU so that policy is running on a small compute factor. And it thinks it's talking to a real robot, but it's actually talking to a synthetic robot, the sensors and actuators of that robot. So that's kind of this full cycle that we need to mature, less of a brittle workflow and kind of an engineering-ready workflow.
More like an enterprise hardened, in other words.
Sure.
Yeah.
And I think in a lot of cases, we talk a lot with robotics developers, and believe me, robotics developers don't want to do DevOps. But a lot of these, and you saw, we have 3 computers, there's a lot of interesting in-depth workflows, things that need a lot of parallel computation as well. And a lot of times, I think having these more automated for them is pretty interesting for sure, and can help speed up a lot of the development cycles as well.
But do we need, Teresa, in your mind, people who have tons of robotics experience, or do you think that there is enough amount of skills out there for anybody to get started? Is that a pain point or a challenge as well that we need to address?
I think robotics is still a complex domain. I think it's easier and easier as we progress to get started. I think in today's world, even with something like simulation or some small robot setups, you can actually get started pretty quickly. Obviously, if you're looking to deploying something in production and have that, you still need some expertise in terms of making these ready and robust in production. But I think in today's world, it's so easy to get started that I think some of these can help a lot, even just broadening the ecosystem and bringing more awareness for some of these topics. We have so many actually kids today doing this that it's actually when I was their age, I was I didn't even know what a robot was in some cases. And it's pretty impressive what you can do even with AI and coding agents today, I would say.
How are you thinking about challenges and pain points from a Wandelbot perspective?
So I think going back to what Aaron was saying, we also have to keep in mind hardware heterogeneity, right?
Yeah.
The workflow, the tool flow that he was describing is great, but in the end, this has to work for all kinds of different robots, all kinds of different hardware. And especially when we look at the more traditional form factors, robot arms that are, ubiquitous when you go into today's factories, they are not on systems that allow for workflows like the ones that Aaron described to just easily flow in, which is also why we focus on what we focus on, because we think that is a major unlock that is missing to have one development environment, one software language that you can work across these different brands and OEMs and bring power into that cycle from simulation to learning and then down all the way to the physical hardware.
So there is no homogeneous, there is no standards in a robotics ecosystems. So it's a very fragmented, multi-protocol, multi-vendor, which typically happens in any enterprise world. It's true even for the robotics.
Very, very true. And I now just focused on the robots, right? When you then think about end effectors, camera systems, PLCs, it becomes even more heterogeneous. And we need to bring that together into platforms to make it more accessible for more engineers and developers to work with robots.
Awesome. So I'm going to switch a little bit gears and think about solutions. Okay, so we understand the pain points and the problems. So Teresa, I'm going to start with you.
Yeah.
From an NVIDIA perspective, how are we thinking about solving some of them?
Yeah, so, and one of the topics that I have not talked too much, but I think this is at least one of the main challenges that I see. And going a little bit back to what Ganesh was saying about the evolution of AI, if you look into the big boom of things like LLMs and ChatGPT, the reason why we had that and even agentic AI is because we have trillions of data available to train these systems. But with robotics, we actually have a big data gap because we simply don't have that data available to train these models. There's a lot of, you can collect some data, and so maybe, a few hundreds of hours or thousands in some cases, but this data is very hard to collect. It lacks a lot of diversity. And even like the hardware that you need to collect this data is pretty expensive. And so one of the things that we're looking at and to solve this sort of problems is how we can turn kind of this data-bound problem into a compute-bound problem. And so for us, one of the key things that we're investing is how can we use simulation and synthetic data generation to solve this. And so the idea is that you will still have a large amount of data from the internet to train some sort of capabilities of vision and language. We have the real data still, it's going to be in general small, but then our goal is really to grow that middle layer of synthetic data. And so for us, we're relying a lot on our platforms like Omniverse to do synthetic data generation. We also have a new platform called Cosmos, which is a World Foundation model platform, which I'm quite excited about, that can help kind of scale the generation of data. And you can use a lot of these, obviously, to train data at scale and to generate that much faster. But you can also use that to even validate. Like you can use simulation to validate a lot of these deployments much quicker than you would basically be able to test in the actual real world. So it's quicker. It can also be safer in a lot of cases. And so that's one of the key things that we're very focused at NVIDIA, is on growing that synthetic data pipeline in order to basically build better models in the end. And yeah, that's one of the key things that I think we're trying to focus on, and I think it's pretty important when we think about going to the next level of a lot of these foundation models for robotics.
Sorry, go ahead.
I totally agree, right? Especially when you talk about simulation, virtual environments, data is key. Synthetic data generation is very important, and there is a lack of data when you compare it to what we did with LLMs. I think there is an additional unlock that we can have there, which is to use data from today's existing installations, right? There's many factories around the globe where robots are operating today that exist in complete silos, where no data collection in an organized fashion is happening, where even the robot controllers are not even accessible to get data from in the first place. And going back to the software platform that brings it all together, that's an additional benefit that you can have when across lines, factories, enterprises, you can start data collection in an organized fashion and learn from that, enriching what Teresa was describing.
So when you're thinking about data collection, is it accessing, exactly as you said, the PLC systems, the robotic control systems, it's operational data of how the robots are operating today? Is that what you mean?
That's what I mean, exactly. The robot controllers, the movements, the programs that they are running, data from for example, the welding torches or end effectors that they are.
So that becomes your training data sets?
Exactly.
Okay.
Exactly.
In a lot of cases, it's also about, even if you have a model, you can continuously improve it with reinforcement learning after you deploy. And so you kind of have a big data flywheel, which is also pretty interesting.
How are you thinking about it?
Yeah, I think this is a good point to build on. Microsoft's platform has been edge and cloud for decades, and we have a lot of experience in IoT. So whether we're pulling data from a PLC or a Jetson, kind of makes no difference. We have the ability to use Arc that we can deploy on the edge, which kind of brings our services down. It brings our identity management. It brings that security. You can layer on top Azure IoT operations, things that provide data plumbing and also workload management and data filtering, so you can get the appropriate data that you want. Bringing that real-world data acts as like the ground truth for some of the simulation data. Hosting sims, we talked a little bit about that. We keep saying training on the cloud, but training on the cloud really means hosting Isaac Sim containers that are running reinforcement learning, that are scaling out the experience of that robot, trying to succeed and being rewarded when it does iteratively succeed. By the thousands, and so they're training and they're experiencing sort of years in the matter of hours, so we can converge on these skill solutions that we're then testing in SIL and pushing down to hill and then deploying. So
Yeah, I think one of the things all of you touched upon is starting with the skill sets that you're talking about, Teresa. Yes, you do require some really hard to find robotic skills, but the learning curve is slowly getting flattened. That's one point. And then the second point is tools are becoming more available on Azure. So if you are a cloud developer, more or less it kind of behaves just like any other Azure resources. That's the same kind of a tool chain that you can start using. And then the third one that you were talking about is that whole heterogeneous systems, but again, it's not rocket science. There are ways to actually harvest those data and use that as a training data. So it doesn't just kind of, for the audience here, we are talking about the future, but the future is not too far. We are a lot closer to the future than you would expect. So there are things that are already in flight, and those are available. So that's truly encouraging. So that's a perfect segue. I'm actually again going to pose this question to all of you guys. So what is kind of the next kind of big shift or moment in the whole physical AI and robotics that's coming our way that we should probably share with the audience as well?
So I see in the next 1 to 5 years, I think that was the time frame that we were looking at, we see a fundamental paradigm shift that's going to happen in robotics, which is we're going to go from deterministic programming of robots, which is the status quo today, to training robots, where we're going to be relying on models, learned policies, and transferable skills that can be moved between hardware systems. And even though that sounds advanced, especially from what we heard today with the different technologies that are being developed, we are fast moving into that direction, and I think that's going to become the new status quo when working with robots, which has the benefit that it will be possible for more people, more engineers, more developers to work with robots than it is today.
That's a great point. So we are moving from the traditional, what we have done for maybe 2 decades or even 3 decades, is programming machines or programming robots to do a certain task a certain way. So if you expect the machine to do something different other than what it has been programmed for, it doesn't know how to do it. In this new world, you're actually training the robot brains. So to mimic as much as possible of what we would actually react and do things differently. So it's actually skills-based rather than actually programming-based. So that's the big shift that's happening as we speak.
And I definitely agree that's going to happen. I don't think it'll be exclusive. So I don't think we're going to go to purely skills-based. All this experience that I have in the industry where they have these streamlined factory lines that are running industrial hardware that are moving extremely fast. I think they're probably going to be still running on ladder logic, but they will likely have some skill. So if they hit a fault, it can observe the fault and maybe potentially recover. Contract manufacturers will probably adopt this even more so. They're going to be shifting. They're often making a phone for 3 weeks, and then they need to make a tablet another week. And rather than spend the money and the time doing this long changeover process when they're not making money, they're likely going to use these skills to say, well, I'm going to train it to install a battery on the phone, and then I'm going to modify that skill so that I can install that battery in a tablet, and then that'll cut down on the changeover time. But with regard to some other things that I'm seeing in the next 5 years that I think is going to have a massive impact is the accessibility. So at the booth, we've had a number of people ask about their kids, if they want to get into robotics, what should they be doing? And they don't need to buy a robot. these simulated environments are so good that they're gonna do a lot of the learning there. Back in the aerospace days, we would have like a SolidWorks, right? And so we would learn with a student edition, and we learned so much there. Kids now can do that in Isaac Sim for relatively inexpensive, and it'll have the same ROS interface as if they're interfacing with a real robot, but it's a synthetic one. And if they have their AI copilot, they can be experimenting with their logic and pretty quickly influencing these extensions.
Weren't you trying that with the VS Code and Claude? You know, just for this, right? You were preparing for that.
Yeah, we were having loads of fun playing with the physics, changing dampening. Yeah, there's a lot you can do there.
Go Copilot.
Yeah.
Shameless plug for Microsoft. What do you think?
Yeah, I would agree with that. And I also agree that there's a lot of work ongoing into these new shifts. I think for some time it's also probably going to be a hybrid. Well, we're going to see a lot of hybrid approaches, which I think it's pretty exciting. And we've seen that already for the past few years, where a lot of the pre-programmed robots were like pretty dumb and blind. And we're starting to add sensors and perception AI, and now going a little bit more into the shift of more end-to-end foundation models, which I think is pretty exciting. In terms of new things that I'm really excited about, I'm very excited about the context and the concept of world foundation models. So this is something that we've, at NVIDIA we have our Cosmos platform, and we started working on this, I think, or released early January this year. And we've seen
that was
so
20 million hours of video trained,
yeah,
right? You probably
around
want to,
that.
could you want to talk a little bit about what that
Sure.
is? Because I think the team here, the audience here would
Yeah.
actually appreciate it.
So basically, world foundation models are models that kind of are trained with, you know, the concepts of physics of the real world. So they kind of understand a little bit, obviously, the physics of the real world, but also things like spatial properties. And this is really exciting because all of a sudden you can actually prompt these models, and they can generate a lot of data. And you can use models like Cosmos to generate data. You can use models like Cosmos even as reasoning type of capabilities for robotics. So as an example, you can have, for instance, a 5-second video of a car going on a lane, and you prompt the model just by natural language, okay, now the car is going on the lane and is going to turn left. And actually, these models generate very cohesive and comprehensive videos that follow the laws of physics. And this is really interesting in terms of scaling that data generation pipeline, but also evaluation potentially. And so there's the whole new concepts of things like neural simulators and world foundation models that I think it's going to kind of be also a big boom in terms of scaling to the next stage of robotics.
So I think if we think about it, the way the panelists just talked about, so there is a heterogeneous, multi-protocol, multi-vendor problem that exists in the brownfield installations, which is 98 to 99% of the factories today. If you think about the technology that Teresa was talking about, there is the whole lack of quality data sets that's required to train robots. So that's getting addressed. And then what Aaron was talking about, making it more accessible, easier, make it available on cloud, because all of these trainings is going to require massive amount of compute. So lower the barrier to get started and to scale, right? So when you put all of that together, I think the opportunity that we see ahead of us is pretty compelling. So with that, I'm going to actually let folks know that there is a microphone. So for those who may have any questions, please feel free to come over to microphone. In the meanwhile, if there are questions that people are interested to line up, I think Aaron already teed up one of the points. Please visit the NVIDIA booth. There's also the Microsoft partner booth. So there is a humanoid that 𝗦𝗽𝗲𝗀𝗀𝗀𝗀𝗀 was actually intimately working on for the last several weeks. It's actually been trained on Azure using Isaac Sim. Everything that we just discussed, it was all done there. So it's something that is a live demo. So feel free to come over. There's also other sessions that we have just to get you guys started on what is Omniverse, how do you build a digital twin, how you think about it. And then there's a joint session that we are doing tomorrow with Microsoft, where we're thinking about how open standards and how do you create truly interoperable systems with standards like USD, which is the foundation for everything that we do in Omniverse and digital twin. So with that, I'd like to thank the panel. Amazing. Thank you for all of you to take the time to attend this session. Any questions? Yeah, please. You're good, you're good.
When you guys were talking about the lack of data to use, how do you think about robotic cars, self-driving cars, and all of the millions of miles that they're racking up? You know, you see the Waymos everywhere here in SF, right? Zoox is launching their thing, right? Tesla's going. So, like, how does that sort of factor into the?
Yeah, I can try to take a stab of it. So basically, an autonomous vehicle is also kind of a robot. So a lot of what we are building and doing for AV is what we also need to do in some cases for robotics. I think as we have this concept of data pyramid for robotics, so I think that real data collection from the real world is still pretty important. And this can be either from teleoperation of robots, or from, like, once you actually deploy the robots, have a continuous loop of actually getting this data. And so this data is still really important, and generally it's harder and more time consuming to collect, but it's the highest possible quality data that you can get. I think what we're seeing in terms of speeding up that development of robotics, that's generally not, you cannot basically get to the level of a robust enough general robotics policy with just that, and that's why we're also focusing a lot on the base layer of that pyramid, which is like things like internet-wide data, but also then the synthetic data. But the real-world collection, as with AV, it's also still pretty important in my opinion, and it's really the highest possible quality data. And so we have, and you're seeing some of the big companies have these concepts, right? So they have teleoperators collecting data from real robots. There's some issues with that in terms of diversity of data as well. It's even hard to collect good data in some cases, but a lot of cases it's also hard to build a good enough diverse data set. And this can be perceptual type of visual differences, but also, you know, objects and other types of tasks. And that's where I think bridging the gap with simulation can help. But as with AV, I think we're seeing that you need the real world, and you also need the simulation, the cars running for hours in simulation, capturing data in simulation, as you need also with some of the real world data.
I'll give you another concrete example to what Teresa was saying. So let's say that there is a really rare data pattern that you want to train the robot brain, in this case the car. Let's say that it is snowing, it's the middle of the night, dark streets, and you want to actually simulate an environment where a reindeer walks in, right, as you're driving. How does your robot brain actually, that the car is going to actually react to? You cannot really, it's a I wouldn't say once in a lifetime, but it is a rare event that's not going to happen here in California. But how do you train a car's brain to all of those conditions? So that's where the synthetic data and the whole different scenarios that you can do. It's cheap, it's fast, and you can train that. But it's not just that. You also need the real world data. So that's where you need to augment both sets of those data.
Yeah. So I'd say there's like expert trained teleopt demonstrations where they're deliberately trying to create imitation learning, maybe a manipulation task, and they're collecting that data set and they're labeling it. But with these cars, they're also streaming at a low frequency information about the car, and it has like a rolling buffer. So if a robot fell down or experienced something random that hasn't seen before, maybe that rolling buffer would be sent up and then be used for training. I could see that happening. It's not something we've implemented just yet with any of the partners that I've worked with, but I could certainly see collecting from kind of the wild. If the robot experiences something unexpected, then it will send that buffer of information up and can be used to fine-tune the model, and now it can manage that corner case.
That's a great point. Any other questions?
I had a quick question. I'm trying to figure out how will agentic AI transform the robotic space. I understand like World Foundation models and VLAs and all that stuff, but in terms of like programming and coding and stuff like that, how will agentic AI transform robotics?
So I think we have already started to work into that direction. When you bring different robots from different manufacturers onto one software platform and make it feasible to have them in one developer environment and program all of them in one software, in one programming language, which in our case is Python, all of a sudden plugging in tools like Copilot becomes very feasible and yields very good results actually. So that's starting to happen, and again, that's one of the benefits of using a uniform platform for different robots, where this then becomes a reality that really takes away or eases the workload of developers and takes away some of the burden onboarding onto robot programming.
I'm actually curious to hear from you so that we have these various vendors with their different robots and they kind of speak different languages. Do you use AGI to help create an abstraction layer on top of each of them so that you have a single API and you can communicate with all? Is AGI helping write that?
Not yet, but so far we've built them in traditional software development. But of course, with every integration that we complete, also our own knowledge base grows, and that becomes feasible. But yes, you mentioned it, right? So at the end of the day, what you have is one unified API for 300 plus robot models, a Python SDK, a VS Code extension with a Copilot, and you're talking about agentic work for robot programming. That's a reality that is possible with Nova.
And that also lowers the barrier again. So, more adoptions, making more accessible to more diverse set of developers to start adopting it. So.
Absolutely, and we have actually one great story there. We recently had an intern join us who's had a good software development experience, but had never seen or worked with a robot before. And onboarding him on Nova, and also, of course, using tools like Isaac Sim and Omniverse, within a week, he was showing us how to improve our demo cells. And that for us is really how powerful these new tools are to bring robotics to more people and more developers.
That's pretty amazing. That's pretty compelling. Any final questions before we wrap up? Yeah, please.
Hi, I was wondering if you've seen use of kind of the first layer of maturity on that curve that you showed, perception, integrated into the feedback loops. Particularly, I was wondering about DeepStream from NVIDIA, like the video perception streaming service that NVIDIA has offered. I was wondering if you've seen that be integrated in your robotics deployments, I think.
Oh, absolutely. I think, and I was talking a little bit about this journey as well in robotics. So a lot of the robots that we initially had were very automated, right? So they didn't have any sensors or any or something like that. And so basically you can, pre-program the path of the robot, but you cannot do anything else. And so the next stage after that, even before you go to these more complex tasks like vision language action models and VLMs and so on, is actually a lot of these robots already start having cameras and lidars. And so the idea with that is even things like doing object detection or pose estimation. And so bringing that perception in where you can understand a little bit the variance of the environment, it's kind of giving eyes to the robot in a way. It's definitely where, and there's already quite a bit of deployments in production, I would say. And the idea is really to make the robots a little bit more flexible, particularly to things that change in, like, a lot of these domains have a lot of different, like every day is different in a warehouse. There's a lot of moving things, there's a lot of lighting differences, packages change, and all of this is really hard on robot or classical robot programs. And so there's a lot of integration already with more classical AI approaches. And this can be on the robot, or in case of if you're even having a large warehouse or it might have multiple cameras, maybe building some sort of fleet perception in terms of understanding how to route robots. So I think these are things that people are actually already doing, I would say. There can and are perfect applications of AI in robotics already.
Yeah, so primarily manipulations and perceptions are like two fundamental building blocks for building a true holistic robotic system. So yeah, so we are already using that. We actually invest a lot of that. In fact, I think Teresa or somebody in the panel actually said that we look at every machine or even actually a space like this as a system with sensors and eyes that we need to we actually even think about this as a robot as well. So we need to
call it outside in.
Outside in, exactly.
AI. So basically the cameras are like kind of, a camera is a static AI system in a way. But these can be really interesting for more generalized type of fleet knowledge and insights. And so for us, that's definitely part of the whole physical AI.
Yeah. We didn't touch about Metropolis, but that's the other aspects of it as well, which is the other stack that we are very intimately building as well, which uses a lot of camera systems too. So this was great, folks. Thank you so much for your time. This was great. Thank you, panelists. Thanks a lot for your thing.
Thank you.
Thank you, everybody.